Hi, my name is Boddie. I'm going to talk about 3 more Cortex-M Inferno ports. So, before the workshop last year, I finally managed to get Inferno running on a microcontroller fairly reliably. And when I say microcontroller, I'm talking about an STM32 microcontroller, which is a 32-bit microcontroller, and it's got a fairly luxurious amount of RAM and flash memory, and the processor is not a very slow thing. It's quite a performant CPU. It has 192 kilobytes of RAM and a megabyte flash memory, and the core that runs it is a Cortex-M4 core, which has some floating point support as well. The instruction set it runs is the Thumb2 instruction set, which is a hybrid instruction set in a sense, because it's designed for code density, and so some instructions are 16 bits wide and some are 32 bits wide. It's related to the original ARM instruction set, and there is some overlap with instructions, but it's a bit more complicated than that, and it probably makes writing compilers harder than they need to be. This microcontroller has just about enough RAM for a tiny shell and some tiny programs, and I was using it to experiment with SPI to drive screens and flash memory, and in a sense you could use it as a replacement for things like Arduino, but it's a bit higher end. Maybe it could also be used for sort of, I don't know, more higher end tasks as well. Not the sort of simplest microcontroller tasks, but maybe something which is between microcontrollers and regular processors. This port is a bit like the ARM ports in the Inferno tree, except it's a bit different. And one way in which it's different is the way it does task switching. So the task switching uses this approach with these two functions, setLabel and goToLabel, like many of the other ports. But the way that this is done for this port is a bit more complicated than the regular ARM ports. And this is really because for the ARM ports, they can perform tricks like changing processor modes. So if you have a timer, for example, and an interrupt fires as a result of the timer, an exception is raised on the processor, and as a result of that, on classic ARMs you would be in a particular mode, and what they would tend to do to handle this would be to switch into a regular mode, I think supervisor mode, and then perform some task switching as normal. But in the Cortex-M4 cores, it's not really possible to switch between modes in this kind of ad hoc way. And that's because Cortex-M4 cores have two processor modes really. One is a mode for running normal code, which is thread mode, and when exceptions occur you have code running in handler mode. And there isn't really a way to switch between the two, so you have to basically return from an exception to get back to thread mode. And this is where things are a bit different to the classic ARM ports, because what we do here is we return into thread mode and then we run the code to switch the tasks. You have to be a bit careful with this. I'm not sure I've really covered all the corner cases, but it seems to work, and it probably needs a certain amount more testing. I started writing a documentation for this that I put on GitHub, and it would be good if people with expertise in that kind of arm or thumb processor area could look at it and sort of tell me if there's anything I've really done wrong, or ways in which it could be done better or made more robust. So last year I talked about frozen modules, frozen limbo modules, and this was basically a way to reduce RAM usage at runtime by taking disk byte code, and instead of having it processed when modules are loaded and run, pre-process it at compile time, keep it in flash memory as much as possible, and yeah, basically just try and reduce the amount of effect on RAM usage, reduce the number of allocations. So one side effect of this was it also reduced the startup RAM usage, because various data structures that would otherwise be copied into RAM at startup no longer needed to be copied into RAM, and so they could be kept in flash memory. And this was an interesting thing for me, because I hadn't really thought about just trying to reduce the overall startup cost, and it made me start to think about ways to reduce RAM usage just generally. So one of the ways I looked at was one that was already in the toolchain, which was an option, a -t option in TL, to allow string constants to be compiled into the text section of the binary. So I looked into this and tried it, and it didn't work for some reason, and so I started to look at it in a bit more detail, and I found some ways to tweak it to make it do something which looked reasonable. And it turned out it had a fairly large effect on the RAM available. In one case that I looked at, it increased it basically doubled the amount of available RAM. But although this sounds quite substantial, this approach overlaps with other approaches that I was taking, like the frozen module approach, and so the effect isn't typically as large as that, but it's still significant. And the other side of this is it also really complements the frozen module approach, because this basically just reduces the startup RAM cost, whereas the frozen module approach isn't made redundant by this, because that still reduces the runtime RAM cost. It reduces the number of allocations. Another approach about saving memory, it's not really so much saving memory per se, but it was an experiment to just reduce the number of memory pools in use. So there are 3 memory pools usually in play: main, heap and image. For our purposes, image is not really very useful because we're not using a display. And usually what has to happen is we decide in advance, at compile time, what the proportions of what the memory proportions are for the main and heap pools. And this is fine for large systems, but for systems with not very much RAM, that can cause problems, because you could run out of one or the other of those pools fairly easily, even though there's still free memory in the system. And in this case, if we just use one, if we basically alias the heap pool to the main pool, we just have one pool and all the allocations come from that. I'm not really sure how safe this is. I realize that you really need to kind of make sure that the main pool doesn't run out of memory. So I suppose there's the danger that certain things that would normally use the heap pool could exhaust the main pool, but it at least allows some things to run on smaller systems that would otherwise be not possible. Another memory saving approach that I briefly looked at was finding constant structures or immutable structures and moving them into the text section as well. And I had some difficulty with this because it's not very easy for me to see how to do that with the toolchain. I spent some time looking at the compiler and the linker loader just to kind of see where information gets propagated and if I could pull things out at certain times like the string constants are. So in the end I just resorted to a quick hack to check symbol names for things which I knew were read-only, and it turned out that if I move some things like lookup tables into the text section, it saved a few kilobytes more. So it may or may not be worth it, but it's useful to look at this a bit more, really, because things add up, and for small systems that's quite useful. So another area that I was looking at was just updating the toolchain for things like floating point instructions. So Cortex-M 4 cores have I would say modern ARM instructions for floating point. Unfortunately they're typically just single precision, and Inferno uses double precision. So the question is how useful they are. It turns out that some of them sort of overlap, so moving doubles into and out of memory, you can have instructions for this sort of thing, even if double precision arithmetic isn't supported. In any case, I borrowed a lot of code from 5L, moving it into TL, and I had to convert what it generated to thumb2 representation. I mean, really, I think with this you're just swapping around 16 bits, the first and last 16 bits of a 32-bit instruction, which is not particularly helpful. The way I did it was arguably not the best, and it could be made a lot closer to 5L. There were a couple of other issues. One of them was to do with converting double to long, where the endianness for the doubles was somehow different for thumb2. And I think there was also a case where there was a missing definition for a temporary floating point register, although I may have removed that. Also, what I had to do was disable registerization in libmath to avoid a compiler issue, and this may be also a problem that faces other ports as well. And with floating point instructions, the other area we have to look at is how to implement or how to handle unimplemented floating point instructions. So for many of these Cortex-M4 cores, they only support single precision instructions, even though there is an overlap with double precision for certain operations. So there needs to be code to handle undefined instructions, and this was done by basically taking the existing ARM implementation and creating a variant for thumb instructions. And since they share the instructions more or less, this was quite straightforward. And then it was a case of testing that they did what they were supposed to do. So I created a simple test program to perform various different kinds of instructions, and I also basically created more decorative and frivolous tests for this as well. And there are some notes and commentary about the way I handled this on the site that I mentioned before, where I'm trying to document parts of the implementation of these ports. and also in the diary that I keep for things that I do with Inferno. So about these new ports of Inferno to microcontrollers. All of them are ports to SparkFun micromod boards, but they could be easily adapted to other similar boards. It's just that it was convenient to use the micromod system for this because the processor boards and the carrier boards are interchangeable. So the first one I looked at after the STM32 was the Atmel SAMD51, and this has 256 kilobytes of RAM, which is arguably a better starting point for porting Inferno. I didn't get into porting Inferno to this very well when I started, and ended up going off and looking at the STM32 instead because I found it a bit daunting. But once I'd done the STM32 port, I realised that this one wasn't quite as frightening as I thought it was. So actually getting it to work was a lot quicker than I imagined. The next one is the Artemis module, which has an Apollo 3 core from Ambic, and that has 384 kilobytes of RAM, which is quite a bit to play with in many respects. It gives you a bit of freedom to experiment. It has a Bluetooth module, and I haven't really figured that out yet. I've been looking at code in the Arduino libraries and framework because they have examples for how to try and do various tasks with Bluetooth. The Teensy is actually a bit more, a bit of a bigger CPU. It has an IMX CPU, which is actually more like an SoC, and it's a Cortex-M 7 core, which is somewhat higher level than the M4 cores that I've looked at. It has a megabyte of RAM, which is pretty useful, gives you room to stretch your legs, and double precision floating point support, which actually means you don't really have to do anything at all with emulating undefined instructions. Some issues remain with all of these. The Teensy has some issue, I think, occasionally with lock loops, so I need to really look into that a bit more. And the SAMD51 probably has issues, but I can't really investigate those anymore because the board I was using stopped working. I've tried to document as much as I can of the way the implementation works for all of these, and yeah, I've provided links to all of these ports in the documentation that I've been writing. So alongside porting to these other microcontrollers, I've also been looking at the different peripherals, the different hardware buses and things like that that each of them supports. The first port, the STM32, obviously has some support for things like the UART and status LED. I got into doing things with I2C and SPI, so external flash memory, and doing things with ePaper. I didn't really do very much with the SAMD51. UART and LED were basically there at startup just to test it. I was doing things with USB and then managed to cause the thing to fail, possibly. The Apollo 3 on the Artemis module, again, the usual things to get going with, and I then started bringing across support from the STM32 to do similar things, except I also looked at an LCD screen as well. I haven't really done as much with the Teensy. I think that is more of a platform for potentially messing around with the just-in-time compiler, given that it has a lot more memory to play with. I did initially start looking at the just-in-time compiler on the Apollo 3, but I'm not sure I had enough memory to play with there. And the implementations of how these devices and how this hardware is handled can be quite similar between the different peripherals and on the different ports. And so yeah, it's quite interesting to play with bits of hardware here. A lot of this is handled with file systems, and there are existing file systems you can just use for things like I2C, also I think SPI, but for many of these things where you have a screen, it's quite interesting to think about creating a file system where you expose, let's say, a data file that you just write to, and maybe have some sort of higher level code to actually send the data to the device, instead of exposing the SPI interface directly. It's arguably more rewarding to do things with things like e-paper, especially with the devices like the Artemis module, because that's supposed to be quite a low power device, and so it makes you consider applications where you could build solutions which are very low power. With 3 new ports, there's a certain amount of duplicated code between them. This is because when I create a new port, I typically take one that already works and remove board specific files from it, just keeping the core files and the build files, and just try and get it to work. But this means that there are common files to all of them, or there were common files to all of them, and a fair amount of common code. And what I wanted to do was really just tidy that up and have a common place for all the, for example, Thumb or Cortex-M code that they could all share, and so they wouldn't have to have individual copies. So I created a Cortex-M branch for this, and I put common code in a Cortex-M directory, like the historical SA1110 directory for all those different boards and devices that had strong arms in them. The SAMD 51 port is still separate because the board that I have no longer works, and I don't really have much desire to revisit that at the moment. At some point, if I get another board which is compatible, I may merge it in with the others. But you can check out the Cortex-M branch to see what I've done, and hopefully this will make porting new boards, or porting Inferno to new boards that are related to these, slightly easier than it would have been. So what's next? Well, the first thing I'd like to do is measure the sizes of read-only and writable data structures. This should help me figure out how much more memory I can save and how much more RAM I can play with on various microcontrollers. So this means basically looking at ways to keep read-only data in flash memory. One of the other things I'd like to look at is to make the task switching a bit more robust. I'm fairly happy with it at the moment, but I have begun to realise there are things I haven't considered. So there are some things I need to look at, and I shall be looking at some of the other ports to see what they do in certain situations. Try and make sure that I've implemented all the things that I should have done. So we'll see if that breaks things, and if I have to rethink how I've implemented it. Another thing I really want to do is to document how things were implemented for these ports a bit more than I already have done. I've started to do this with the collection of documents that I've put up on GitHub for things like floating point support and for task switching, but I really want to kind of broaden this out a bit to have much more information for people who want to try and do similar things. And I'd like to look at possibly doing some more ports to other related microcontrollers. It would be interesting to consider other architectures as well, but that really depends on compiler support. I know that there is some RISC-V support, there's a tool chain for that, and it would maybe be interesting to look at the extensor architecture as well on the ESP32 processors. Finally, there are some resources that you can look at. There's a related paper for these slides, which contains a bit more information, especially about memory usage. I created a site which I called Inferno Ports. It's just a GitHub site really, that contains a list of different ports, that not just the ones I've worked on, but also the general Raspberry Pi port. It contains links to them, links to the instructions for building them, and also in some cases links to downloadable files to actually install on them. And there's a related Inferno Ports documentation site which tries to cover the implementation of, well, especially these Cortex-M4 and M7 ports. I also have a diary which I update from time to time to help keep me going with Inferno, and I've talked about some of the issues that I've mentioned here in that. And there is also my presentation from last year, which gives a bit more background information on the work that I did with freezing Limbo modules. Thanks very much for listening.
Does anyone have any questions? If so, then please come here and take the microphone.
So I've played around a lot with these kinds of embedded systems, and I'm very curious how you're actually getting the code onto the devices. What kind of tool chain do you have to flash the boards and so on? And even better, is it possible to run it on Plan 9?
Okay, so to get the code onto each of these boards, it's usually fairly straightforward because they usually have some kind of bootloader that lets you use either the UART, or they do something with they typically have USB connections, or USB-C. But it's basically, I think, a UART or serial connection for all of them, even if it goes via USB. I'm trying to remember, it's different. Unfortunately, it's different for all of them. But some of them do use some fairly standard tooling, this DFU stuff. And as to running things on Plan 9, the tool chain probably runs on Plan 9. And I think someone has been pulling stuff back from the Inferno TL, for example, back into 9front, I think.
Yes, I think I ended up pulling the thumb linkers and compilers from back into 9front, using it for targeting the GPA, and I ran into that same problem that you did about wanting to classify these global data structures as read-only, so that you could put them in ROM instead of having to load them into RAM. Is a lot of disparity in the amount of size for both of those. What we ended up discussing, and we never ended up implementing, was finding, carrying the information about what was declared as constant. I know it's not typically something we do in the code as is, but it might be useful for this application about preserving the information, having things marked as constant. Okay, that goes in the read-only data segment. And that's just something we were thinking of. So I was kind of curious to see if you had considered that, or kind of that chain of thinking for that.
Yeah. What I did was I went into it and looked at the compiler. I'm going to say the compiler. I think I was looking at TC and TL basically. And what I found interesting was that, is it const and static are both considered garbage words or something. So you don't really get the information about those once the code gets as far as TL. as far as I'm aware. I then started to think about, I think I have some diagnostic code where I look at the sizes of things. And I started to do tricks where I was basically just looking at symbol names. So for example, you have all the error strings, which are not constant strings. When I was talking about constant strings in the presentation, they're basically literal string constants in the code. But for example, the error messages, they are defined as character arrays somewhere. And I realized if I did a quick hack where I did a string comparison on symbol names, you can pull all those into the text section. And I did that with lots of different structures. I started identifying things by the names and was seeing what would happen if I moved them out of data into text. And for some of these things, they need to be written to a runtime, so that breaks things badly. One thing I was thinking about was basically trying to reintroduce some kind of qualifier that you could add to the code to say this is something that never changes. I think at last when I looked at like Arduino programming, they had this prog-mem macro or something, and you could probably decorate lots of things with that. But I don't really want to go into the general Inferno code base and just start adding something like that.
I wonder whether the compiler could actually mark things as having been written, since it does in some sense know it has to compile the code. It knows when something's in a writable context in an expression, for example. And if you get to the loader without that attribute being set, you could then decide to put whatever it is into the your flash memory or read-only memory or whatever it is.
Yeah, I think that's what I wanted to. I just couldn't see how to do it in a very quick way. I didn't really, I have to say, I don't have a very good understanding of the way the compiler works. So I was effectively tracing through a lot of symbols and looking at data structures and trying to see if it has that kind of information and passes it through. And I think there's this kind of barrier through which it doesn't propagate some of this. But I don't know. I think it takes a lot more study before I can understand that.
Yeah, I was going to say that the advantage of having the compiler do it without attributes is that, well, first it will then find them all, or a great many of them, and you won't have to worry about adding the attribute. The other is that const has the disadvantage, like async await, of propagating throughout your type system the way that C defined it, or ANSI C defined it. Whereas the compiler at some stage has an AST form where the names are still visible and what you're doing with the names is still visible, so that it might not be too hard to set it up so that it marks a name as having been written to, including indexed names, or the base name of an index name, A sub B, and then the later stages, provided that information is carried through in some way, which probably isn't too hard to add. Then the later stages, such as the loader, can use that information in order to decide where to put things, and do that automatically for you without having to touch anything else. So yeah, I'll think a bit about that. I mean, it's much. One has the program in a not too bad a form at an early stage. It probably could do more along those lines to aid implementations like yours. I mean, it's one advantage of having ownership of the tool chain, really.
Yeah, I think It looks like someone tried to do something like this before when I looked at the implementation, because I think there are some enums which are not used for describing different kinds of like text or data. I think is something which I would interpret as talking about constant data or something, and it's just not used. So it seemed to me that someone had thought about this before, but not really implemented it or something. So
yes, I mean, we went through a phase of doing some things with quite small boards, but then the targets we ended up working with commercially ended up being a little bigger, and so we didn't have to do things. In fact, even the thumb mode was only added as a kind of commercial requirement, which they then didn't pursue because it's on the target that they had. It was actually rather silly compared to the things that you're working with.
yeah, but it's in the end it was good that it was added because it's effectively mandatory now for a certain level of processors.
Yes, indeed. I mean, at the time we were anticipating that ARM's various circuitous ways of adding more variant, well, not even variants, completely different architectures for each of the processors, and then deciding that they would go with something much more conventional with the thumb stuff.
Yeah, it's quite a mess with all that now. I mean, it's almost a case that you have systems that will support the thumb mode and 64-bit, but not really 32-bit or something. It's quite bizarre, really.
Yeah, so at some point they forgot that they had a 32-bit architecture already there and then invented another one. But it's quite impressive how much work you've been able to do on that to get all that stuff going.
Thanks. It's amazing it actually works in some ways.
Right, so nobody dares to ask more questions. I can just confirm from my side. Oh, Ron has a question, but you need to get up here. Oh, microphone is here. He's coming.
I guess it's on your website, but I was just wondering where you get the e-ink display.
I think I got it from, the e-ink display came from Pi Moroni in the UK.